Hello guys, and I welcome you to today's tutorial. So this is a question from material science, specifically on the topic crystal structure. So this is actually one of the most trickiest question they can ask you on an exam. I got this question from a paper. Without wasting much of your time, let us just go through the question and try to see what they're asking for. So atomic packing factor is just given by Vs over Vc. So what is Vs and what is Vc? So in this case, Vs, we're just talking about the total volume of the atoms that are occupied in a unit cell. Vc, we are referring to the total volume of that unit cell. So in other words, atomic packing factor is a ratio of the volume of atoms that you actually have in that unit cell compared to the total unit cell volume. So with that said, we need to know what Vs is and Vc is. So for such kind of a question, it's always ideal to say, step one, we need to know first and foremost how many atoms are contained in an HCP crystal structure. So yeah, we can do just that. Let me just begin on your page. And so a rough sketch would look like this. Let me just quickly sketch it. Yes, so I've quickly done a rough sketch so that you can easily understand. So this is how atoms are arranged in an HCP crystal structure. So how do we determine the number of atoms that are contained in an HCP? So with that said, we just need to know that this is just a small portion which has been obtained from an infinite number of structures of this nature. So you might as well assume that there is another crystal on top like that. Actually draw it, and there is also another one this side like this, also another one that side like that, and another one on top like that. So if we consider, for instance, this atom here at this corner, and we want to know how many number of crystals are actually sharing that atom, we realize that it is actually going to be shared between 6. Yes, there will be 6 in total. I know you can't clearly see it from here, but a very visible diagram would actually entail to say there will be 6 atoms which are sharing. So that would be, considering this section of the crystal, we would just say that will get a portion of 1/6. Then how many corners does this crystal structure have? It has 6 on top, 6 down, so that makes 12 in total. But that is not the only number of portions of atoms it's containing. Notice that it also has an atom on top and an atom below, but that is not a full atom. It is actually being shared by a crystal on top and the one below. So in other words, it is only getting a portion of half, multiplied by how many? 2, because there are 2 atoms here. Again, that is not the only number of atoms. We also have 3 atoms at the center there. So it means the number of atoms, in this case, it would just be here 1, 2. So you get 2 plus 1 plus 3. 2 plus 1, 3 plus 3, you get 6. So that is your step 1. You first need to know the number of atoms. So let's move on to step 2. So once you have determined the number of atoms, you now need to move on to the next step. So for the next step, you just need to get a relationship. It's a relationship. We normally denote this by C to A. So that is what we need to do next. But how can we obtain a relationship for C to A? Still, we need to go back to this thing we had drawn here. So we can say maybe we can slice out a portion, this section here. And notice that we're doing all this simply because we do not really want to start working with a hexagon, because from our mathematics we don't really know much about an hexagon. Do we know the area of a hexagon? No. Volume of the hexagon? No. We can calculate it, but it might take some time. So, especially given the fact that this is actually in 3D. So we just don't want to work with that. We want to work with shapes which we are familiar with. So let us just do that. So if we do that, we can just redraw that cuboid. I don't know if it's a cube. Look something like this. So now notice that there are corner atoms at every point, including there. But also notice that there are 3 atoms at the center. So what that means is that because we have just taken out one slice, it means there could be another section of this nature and another section of this nature. So with that said, it simply means since there are 3 atoms at the center, one of them is here, one of them is here, and the other is here. So it means this portion only gets 1 atom. So now let us name our lattice parameters for this section. It means this portion will be denoted by A because we have an A here. And the height, in this case, it will just be a C. Yes, even this section, it is the same as A. Yes, just like that. So from here, we now need to come up with a way in which we're going to determine this ratio, C to A. So one way we can do that is by simply saying we can connect the middle atom to the edge like this, and also to that atom. So by doing so, we obtain a shape of this nature. Which has a there. So now perhaps it's going to be convenient for us to just randomly label these edges. We can just use J, K, and maybe we can call this M and L. Apart from that, something else we want to do is we want to denote the height, but notice that this is somehow slanted. So perhaps the height is, you need to drop this and it drops here and you connect it to this corner, meaning your height in this case, we got this atom at the center, and this atom is just situated halfway through C, so we can say half of C, or C over 2. So with that said, we can continue from there. So we want to take out another portion. So by the way, let me just call this point H. Yes. So now let us take out the bottom triangle. So that is JLK. So let's see what we can get from there. So that would just be J, K, and L, like that. So we know that this section is just A, but then we want to locate this point H. So this point H will just be at the center there, H. Maybe we can connect this to J like this. Now we can even drop this on the base of this JK, because notice we are simply about to determine the area of this section here. So because this was A, if we drop it just at the center, it's going to be half of A, so it's going to be A over 2. So because this section here is actually an equilateral triangle, we can say this whole angle is 60. So this line passes just at the center of it, cutting the 60 into 2. It means this angle is now just 30 degrees. Yes, so that is what we obtained from there. So maybe let me just start a new page. I'll get back to that. So from there, we notice something. We can take out another portion from this shape we have obtained here, but this time around we want this section, which is a right angled triangle. So we can do just that. So now notice, if I rewrite just this section alone, I can draw it. It's just going to be a right angle triangle. And notice that this point is J, and the middle point is just H, top point is M, just like that. So with that said, from this one we can just use the concept of Pythagoras theorem, which we are all familiar with. So it means we can say Jm squared is just equals to Jh squared plus Mh squared, like this. So notice the goal is to find the ratio C over A, but we're just going to try and use this, but eliminating all this Jm, Jh, and Mh. But we just want to have C and A as the two variables. Yes, so what can we do from here? We can simply, first and foremost, notice that Jm, because this is more of an equilateral triangle, this is also A, this is also A. So it means this is A squared. So we have eliminated the first term, but we just want to have two variables, C and A. So we need somehow to eliminate this as well, Jh squared. So Jh, how can we eliminate it? We can use this triangle we had formed, the smaller one, with an angle of 30 degrees, because we've seen a relationship it has with a over 2 here. So if you rewrite that, let me just quickly rewrite it. It was also a right angle triangle, 30 degrees, and this point is a over 2 j, and this was h like that. Yeah, so let me not label that point. So we just want to obtain a relationship with jh to a over 2. Notice that this is in fact the adjacent of this angle, and this is the hypotenuse. So we can use the ratio. Cosine 30 is just equals to the adjacent, which is a over 2, over the hypotenuse jh. You can cross multiply, and if you do your calculations very well, you just get jh is equals to a over square root of 3. Keeping in mind that where can I write from? Cosine 30 is in fact just a ratio, and this ratio is square root of 3 over 2. Keeping this in mind, of course. So let me just rub this. This, I don't really need it. So we have jh squared. We can easily plug it in there as well. So this would just be a over square root of 3 squared plus. We now need to get rid of mh. So we do as wise. So for mh, we still come back to this diagram we had made there. Notice that we are mostly getting our variables from this diagram. So mh, I don't know if you can see the h. This is simply just the same as the height, which is c over 2. So we can put c over 2 there, then square it. So almost done. Second step of getting the ratio c over 2. So we just need to somehow manipulate this and make sure that we make c over a the subject of the formula and everything else on the other side. So if you square, you just get a squared over 3 plus c squared over 4. And if you do your algebra very well, this is simple mathematics. You just end up with c over a is in fact equals to the square root of 8 over 3. Now you are done with step 2. So the next thing which you have to do is just manipulate this and plug into the formula. But for this particular question, we are not yet done. Just a moment. So we know that atomic packing factor is equals to the volume of the sphere divided by volume of the unit cell, like this. So with that said, we need to know what these two volumes are, but we have just obtained a ratio. So notice that we can even rewrite this to be c is in fact equals to 1.633 times a. It is the same thing if you punch it on the calculator. So that said, we can try to work out something from there. So volume of the sphere, which is just the same as the volume of the atoms which are inside that unit cell. I think we explained this at the start of the video. So when we have a sphere, we remember from mathematics that a volume of a sphere is just 4 over 3 by r cubed, like that. Not so. So, with that said, but this is the volume of one sphere. Recall, we said there are actually 6 spheres, which is what we obtained from getting the ratios of the shared atoms. So 1, 2 times 4, we just get 8 by r cubed. We have obtained this thing here. But what about the volume of the unit cell? So that is going to be a bit tricky for us, but we just need to do it. So the best way we can do that is to set new parameters again. So maybe we can say we just take a look at the top face of the hexagonal close packed. It looks something like this. Notice there are 6 atoms, like that, and in fact they should be touching each other, but even just like this is fine. So if you try to connect them, you notice that they're just connected like that. Yes, so now we can label all these 4 points. Maybe this can be the origin, or then we can start with A, B, C, D, E, F, just like that. So with that done now, we want to take out just one section from these smaller triangles which we have formed. Maybe let's take a look at this portion of the triangle. Let me just take out that portion and start a new page. So we have picked out that triangle there. Here's A, B, and you have your O there. So we notice that the edge length is just, in fact, A, right? Yes. So it means this portion is in fact A. And because this is an equilateral triangle, it means the angle is just 60 degrees. So maybe let's take out a section here. So we just want to determine the area of this triangle, AOB. So maybe you can use the ideas you have from vectors and how to determine area of the triangle using the vector method. So notice this is given by 1 over 2 times the magnitude of AB times the magnitude of OP, then times sine theta. This is a formula you have from your mathematics. So it means the area is going to be 1 over 2. The magnitude of AB is just A. Then the magnitude of OP is also A, and times sine 60. So if you punch in error, you realize that you just get the square root of 3 over 4 times A squared as the area. But notice that we want the volume, not the area. So with that said, we notice that volume is in fact equals to base area times the height. So in this case, the height is just C. So volume, and in this case it is VC, it is just equals to square root of 3 over 4 squared times DC. Now we are done, and we can easily plug in everything into the equation. It means APF is now just going to be equals to 8 pi r cubed over this whole term here, square root of 3 over 4, then a squared c. So maybe from here you know that you made a relationship for C to A, because you don't want that C here. We said C was just equals to 1.6338. So you can plug that there. Okay. So you just get 8 pi r cubed over square root of 3 over 4 a squared times 1.6338.